In the last couple of talks, we have been looking at physical considerations, but we've been looking at them primarily, you might think of as external forces on a building. Rain and wind and soils and all of those factors that have to do with the outside in on a building. For the next couple of talks, we're going to be concentrating on physical considerations, but more from the internal side of the building, its structure, its materials, how physical forces work within the building, and how that very much shapes the character of the architecture. So we're concentrating today on structure and materials. This is really in that original Vitruvian triad that we talked about, firmness, commodity, delight. And we took physical considerations from firmness. Well, today we're really talking about the firmness aspect of physical considerations. What makes buildings stand up? How do they become structurally sound? How does that influence the kind of materials they're made of? And so on. So at the beginning here, I want to just give the most baby fundamental sense of how physics work on a building. And for those of you who are in engineering, you're going to think I'm talking baby talk and it's ridiculously elementary. And maybe for some of you who are liberal arts majors, you might say, oh my God, he's gone technical on us. But we're going to try to hit a happy medium here. And just understand in a rudimentary way how physics, and it's actually a part of physics called statics and dynamics, how statics and dynamics affect the structure and the materials of a building. So there are four major forces that we look at when we try to understand how gravity and other wind and other forces work on a building. So those four forces are tension, compression, bending, and shear. And they actually are fundamentally different in the kind of action they have on the molecular structure of the materials that are resisting these forces. So in tension, it's trying to stretch or pull apart the molecules of that material. And we're worried about failure here. You know, we don't want the building to fall down. The building falls down when there's a failure in that material. And in tension, the failure comes by stretching and disconnecting the molecular bonds of that material. The second force is compression, quite the opposite, where we're pushing together the molecules of a material, smashing them. And when they fail in compression, and in a very different way. That third force, which is shear, that's where we're actually just shearing across or ripping across and tearing the molecules in a kind of lateral way across the material like that. And then the fourth force is bending. And this one's very interesting because it's actually a combination of tension on one side and compression on the other side. So when you bend this, it's stretching the molecules on this side and it's compressing the molecules on this side. So bending is actually a combination of tension and compression. Now, when we're designing a building, we're worried about all four of those things in a building. But for most buildings, vast majority of buildings, their controlling forces are compression or bending. And it's only occasionally that tension or shear end up being the controlling forces in the structural design of a building. A case where tension would be controlling would be something like a tent. When a tent has wind blowing against it, you've probably experienced this if you've been camping, and the wind blows against the fabric of the tent and the fabric billows and stretches and it's being pulled apart. And if that fails, it's failing by tension or ripping or pulling apart the material of the building. Likewise, that guy wire that's running in the tent down to the ground, if the wind comes really strong and it pulls on that guy wire is in tension and it would fail by a stretching of those molecular bonds in that guy wire material. So in tents, yeah, tension's a huge factor, but we don't build many tents. So this is not a frequent controlling factor in the design of a building. Likewise, shear, in some cases, this is really important. In an earthquake-prone area, the building is sitting on the ground like this, and if the ground starts going like it does in an earthquake, it creates shear in the building, and that becomes the controlling force in the building. Likewise, maybe a high-rise building where there are very heavy wind loads, and it's anchored to the ground here, and the wind is pushing that way, then shear becomes a very important factor in the design of that building. But again, this is a relatively small portion of all buildings: tents, earthquake-prone areas, high-rises with a lot of wind load. Most buildings, it's really compression that we're worried about, and this leads to a whole genre of structure that we call bearing structures or compression structures, or it's bending, and that's a whole genre of buildings we look at as either bending structures or frame structures. So those are two kind of generic types of structural systems. Now, we also are concerned then with, well, what materials can resist the kinds of forces that we have in this building. So just because of different molecular bonds, different materials resist those forces in different ways. So for example, if we're looking at compressive structures, the materials that are really great for that are something like brick. Brick is very solid and heavy and earthen, and you can put compressive forces on it. It resists it really well. Whereas it doesn't resist tension very well. So think of putting a brick in your driveway and running it over with your car. You can run that heavy car on top of it, and probably if you run over that brick, the brick's going to be fine because it's very good in compression, that's smashing together. But if you take that same brick and you put the holes in a brick, you say put a rope through one hole and a rope through the other hole, and you tie it to two car bumpers and you pull apart, that brick will disintegrate. I mean, it will go in a nanosecond because brick is not good in tension. Its molecular bond does not resist that pulling apart, but it's good in compression. It's fine when you're smashing it together. And the same would be true of stone, which is another kind of earthen compressive material. The same would be true of concrete, which is another kind of earthen or compressive material. So if you've got forces of compression in a building, the materials that would resist that very well would be brick or stone or concrete. Now, that other genre of structures, bending structures, totally different. As we said, bending is a combination of tension and compression. So what you're looking for is materials that are kind of equally good in tension and compression. So wood, for example, because of its molecular structure, it's about equally good in tension and compression. So that makes it good in bending. Steel is fantastic in both tension and compression. So steel is excellent in bending. So what we're looking for when we design the structural system of a building is we're looking at what kinds of forces are there, what kinds of materials are appropriate to use to resist those forces, then what quantity of force is there, and what quantity of material is necessary to resist that amount of force. And that, in a very elementary sense, is what the structural design of a building is about. So we're going to be looking today at a number of examples of buildings where it's very clear that they're using structure as a defining parameter of the building, that this is actually shaping the building significantly. And sometimes it comes when materials are in the lead. They have certain materials to use, so they know they have to keep it to the forces that are good for those materials. Sometimes it comes the other way around. But in all of these cases, we're going to be seeing buildings that are very significantly shaped by the structure and the materials and the way they're put together. So let's start with a very ancient example. This is the city of Hattusha in north central Turkey. This is an ancient, this is one of the oldest examples of architecture. I mean, it's not quite like the pyramids in Egypt, but close to that. This was a city that was the capital of the Hittite Empire, an ancient empire in in central Turkey. And in about maybe 1375, that was the peak of the success of the Hittite Empire. This was their capital. There were 50,000 people living in Hattusha. It was a very sophisticated, very successful city of the time. By 1200 BC, 1200 before Christ, it was destroyed and it was gone. And so it's been a ruin pretty much since 1200 BC. And there are a bunch of German archaeologists who've been putting this thing back together for decades, and it's pretty impressive, although it's in the freaking middle of nowhere and extremely remote in northern Turkey. So here you can see the foundations of these buildings, as we're seeing right there, and they're big, thick, now compressive structure. You can see that the terrain around there, it's almost totally rocks, and there are not very many trees through here. The resource they have to work with is stone, and there's plenty of stone. So they're taking that stone and they're building compressive structures here. They're building the foundation as we see it right there. And then you can see they're really master masons. They're able to carve out that stone very carefully. This is a threshold where you go into a house. You can see how they connected stones together. They didn't so much use mortar like we do today, but they would make a hole in one set of stones, and then they make a hole in the stone above, and they put a peg that would connect those together. And then as the loads came down here, those compressive loads would be working on that and creating the threshold for that house as you begin to go into the house. You can then see how they're building up the walls, and this is a classic way. We get a stone wall. It's compressive forces, stone on stone on stone, those compressive loads moving down through the stones and into the ground. Now, they were master masons. This is incredibly impressive that they were able to work that stone to get these really perfect joints. I mean, you can't get a knife in between that joint. They've cut it so perfectly and fitted them all together. They're master masons. They know their material and they know how to control all those compressive forces and transfer them through the building and into the ground. Now, they're primarily dealing with compressive materials. So what happens when I want to make a door and I want to have a lintel over that door? Now that is in bending. All of this is in compression. But that one now wants to sag like this. It wants to have tension on the bottom and compression on the top. And stone is not good in bending. Now, it's not to say it doesn't have some properties that resist bending, but it takes these massive pieces of stone, and then you can see them corbelling out the stones below to make that span just as small as they can possibly make it, and then use this massive piece of stone to try to do it. They're struggling with putting bending in a building element and only having a material that handles compression that they're working with. And as you look around in the city, you can see where the failure has come is in cases where, as in this gateway, they're trying to make quite a long span. They want a big opening here, and they're moving it up to make that span just as small as it can be, but obviously, it failed because they're using stone, and it was stretching its capabilities to be in bending, when it's not really very good in bending. Now, these people are freaking impressive because you can see their mind working. When they actually made the roofs of their buildings, they did have to import wood to do that because the stone couldn't make a room. It made beautiful walls, it made okay openings, but it really couldn't make the roof. And it was difficult and expensive to bring in the wood to do that kind of spanning and play that bending role. So they're trying with the stone. Is there a way we can use the stone to make a room to span over the space so that we got this in compression and compression and compression, and then we just have the tiniest little bit in bending up there. But they're struggling and struggling, and that's very sophisticated stonework. But that room is just, I can stretch my arms and touch both walls. It's not a very big room, so they're not able to really use their materials and their structure to make the kind of spaces they would like to make. So it's radically affecting their architecture. They're confined to making very small spaces inside. Now, the very same thing is happening way on the other side of the world in the Americas and with Native American construction, all the way from the Incas, the Mayas, the Aztecs, all of these very, very sophisticated builders. But again, they're building primarily in stone. This is a beautiful Mayan citadel in Tikal in northern Guatemala. It was done about 200 to 800 AD. So this is in the middle of a forest, a rainforest, as you can see here. But they're building primarily out of stone. And you can see in the stone work there how sophisticated they are, how beautiful these pyramids are, how when you're doing this, it makes perfect sense. The compressive loads are smaller at the top, getting larger, 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 and that shape and form is coming out of the structure really beautifully. But now, what if you want to make interior spaces? Well, when you just make an opening, they're smart enough to figure out the stone doesn't do this very well. We'll use the wood because they do have wood sitting around in the forest there. So they're making the little, which is in bending, in wood, which is good in bending, but it's a little weird. I mean, the wood is not as long-lived a material as the stone, but they're using it appropriately structurally. And then you see them doing the very same thing as the Hittites were doing, making these spaces where they're trying to cover a room with stone and keep it in compression as far as they can, and then just span a little at the top. Now, that's phenomenal to me that the Hittites and the Mayas, completely separate civilizations, because of the nature of stone and because of the way structures work, because of these physical considerations, they're coming to virtually the same shape, the same form halfway around the world from each other. Now, the remarkable thing is that there is an easier way to do this that neither the Hittites nor the Mayas or Incas discovered. And that is the notion of an arch. Because an arch is a way of carrying those loads around in compression and making a large opening while keeping all of that material in compression. And this really, a couple of talks ago, we talked about how geometry sometimes makes structural sense. Well, this was one of those instances where that portion of a circle was the right answer. And when you get all of that in place, all of those pie-shaped boissures together like that, and a keystone inserted in the middle, then it makes perfect structural sense. And all of that works in compression, and it makes a beautiful masonry structure. And this is Pont du Gard, this fantastic aqueduct in southern France. This just blows you away. The scale of this thing is phenomenal. It basically goes across from one hill to another hill, and it is both a roadway and an aqueduct that carries water across there. You can see those tiny little dots. Those are people. It's a massive, massive structure. And this was built by the Romans. The Romans were phenomenal builders, phenomenal builders. And they really discovered the full capability of that compressive material of stone and how they could make very big openings out of it. But this is a classic application of that, where you get smaller arches at the top and a thinner wall. You get medium-sized arches in the middle and a thicker wall, and massive arches at the bottom and a super thick wall. And you're just seeing that collection of loads as it goes down through the structure. And then at the very bottom, it's even thickening once again to carry those loads down into the ground. But the shape and form of what is essentially here an engineering structure is just to carry those loads in the most sensible way using that compressive material of stone. It's freaking beautiful, but it really is all about just understanding the loads, the materials to resist the loads, the shapes and forms that transfer those loads in the most natural and appropriate way, and that is really determining the character of the Portuguese. Now, as I said, the Romans were freaking master builders, and we look at many of the landmarks in Rome. I mean, maybe the Colosseum is the best known of Roman buildings. It was done in 80 after Christ, 80 years or so after Christ. And you can see in this instance, this building that is really made out of compressive materials. It's made out of brick and stone and rubble concrete. And pretty much all of the building is in compression. And the architecture of the building is really a reflection of the way these things sensibly go together. Massive masonry walls that are carrying those loads. And then when you need to make openings, you use the arch as a way of making that opening. And really, people look at the Colosseum and they say, whoa, the Colosseum is such a beautiful, beautiful building. I love those arches. I love the rhythms of them. They make such beautiful shapes. It's so graceful. But fundamentally, the Colosseum is structure. It is simply the appropriate and natural way to take those compressive loads around the arches down into the building. We can see how it, thinner at the top, gets thicker and thicker as it goes down. All of that is just a reflection of loads and transfer of loads and sensible movement of the loads through the building. And then when you see it in its ruined state, you see that it really is just raw structure. That's the character of the building. And by the time you get to the Colosseum, now they're not only realizing that they can make arches to make these openings, but now they can also make vaults, which is taking that arch and moving it in 3 dimensions to make this kind of tunnel of space. And that inside that, they can make a pretty good-sized room that is created by that vault. And again, keeping all of that material in compression, in this case, brick. Now, but when you do see failure in the Colosseum, because it's, centuries old, where does it fail? It fails if anywhere along that arch or along that vault there's an incompletion of that shape, then the whole thing falls apart, because an arch is only structurally sound when it's complete. Take out one stone, it's worthless. And the same thing is true of that vault. So that has fallen apart because at some point, part of that radius failed, and then the entire thing was no longer supportable. But the point I want to make maybe most firmly in this talk is how fundamentally structure is a maker of architectural form, that it really is a key ingredient in creating shape, form, character, rhythm of architecture, because that's just how architecture is made, and that's how it works. Okay, see you next time.